When we build waste dumps or rock slopes, falling material is not a possibility. It is an expectation. So, an important additional safety feature is the catch bund at the base. Its job is simple: to stop falling material before it reaches roads, work areas, or people. But for a catch bund to work properly, 3 things must be right: space between the toe of the slope and the bund, the right height, and the right width. Yet, at many mine sites, these 3 elements can vary. So let's look at why each one matters. But before we can understand why catch bunds need specific spacing, height, and width, we first need to understand what they are actually trying to stop. Yes, the simple answer is falling rocks, but the full story is more involved. Slopes vary across a mine site. Their height changes, their angle changes, the material they are made from changes, the size and number of rocks that may fall changes. So when we add a catch bund, we are trying to stop rocks falling from height, carrying energy, speed, and momentum that depend on how high the rocks begin to fall, from how steep the slope is that they roll down, how big or heavy the rock or rocks are. A catch bund is a safety barrier, and like any safety barrier, it must match the hazard it is meant to control. To understand that hazard and the energy of falling material, we will reference an analogy many people are familiar with. To understand the physics behind this, let us step away from the mine site for a moment. Imagine a downhill skier standing at the top of a very steep slope. They are not moving yet. Everything feels calm. But something important is already present. Because the skier is elevated above the valley floor below, they possess gravitational potential energy. This is not energy inside their body. It is stored energy that exists purely because of their height above the ground. The higher they are, the greater that stored energy becomes. You cannot see it, but it is there, and it will determine what happens next. The moment the skier tips forward and begins descending, that stored energy begins converting into motion. Height turns into speed. As the skier travels down the slope, gravitational potential energy is progressively converted into kinetic energy, the energy of motion. What the skier feels is increasing downhill speed. Unless they actively resist it, that speed continues to build. A steeper slope increases acceleration. A longer slope provides more time for speed to develop. At a mine site, rock fragments behave in the same way. The higher they start, the more energy they carry. When they fall or roll, that stored energy converts into velocity and momentum. So now we return to the mine site. Rock fragments at the top of a slope behave just like the skier. The higher they start, the more gravitational potential energy they possess. When they detach and move downslope, that energy converts into motion. And once that motion begins, the rock carries both speed and momentum. A catch bund is designed to intercept and contain that moving energy. It is not there for appearance. It is there to manage impact. So far, we have focused on what happens at the top of the slope. We have talked about height, slope angle, and mass. All of these factors influence how much energy is generated. But now we need to look at something equally important. What happens at the bottom? Let us return to our skier. Imagine that after descending the steep slope, the skier reaches a wide, flat area at the base. At that point, something changes. Gravity is no longer accelerating them forward. Instead of speeding up, they begin to slow down. Friction between the skis and the snow resists motion. The snow deforms slightly under the skis. Air resistance continues acting against them. Over distance, these resistance forces reduce velocity. Eventually, the skier comes to a stop. What this tells us is important. If there is sufficient flat run-out distance, moving energy can be dissipated gradually. Objects traveling downhill will eventually slow and stop, even without a physical barrier, provided there is enough room. But what if we do not have that luxury? What if there is no long, flat run-out area at the base of the slope? What if there is a work area or haul road below the slope, and we cannot allow material to keep rolling until it eventually stops? Now the situation changes. We no longer have distance to dissipate energy gradually. We need to stop the movement quickly. So imagine placing a barrier directly in the skier's path at the bottom of the slope. Think of it as a catch bund. Its job is to intercept what is coming downslope. But whether it succeeds depends on one thing: the energy arriving at the base. And that energy depends on two primary factors: how fast the object is traveling and how much mass it has. A fast, heavy object carries significantly more kinetic energy than a slow, light one. That means the bund must be capable of absorbing and resisting that energy. It must be tall enough to block the object and wide enough to remain stable under impact. If it is too small, too narrow, or too weak, it will not perform. The incoming energy will overwhelm it. So now we bring this back to the mine site. A catch bund is not just a pile of material at the base of a slope. It is an energy management structure. And for it to work properly, three things must be right: height, width, and distance from the toe of the slope. Let us look at why. Firstly, we will look at height. The bund must be tall enough to physically intercept the rock. If the incoming rock has sufficient velocity and the bund is too low, the rock will simply ride up and over it. Second on the list is width. Stopping something is not just about blocking it. It is about absorbing energy. When a rock impacts a bund, the bund must be wide and substantial enough to resist sliding, shearing, or collapsing. Then thirdly is the distance from the base of the slope. This one is often overlooked. If a bund is placed too tightly against the slope, rocks do not have sufficient space to land within a controlled catch zone that keeps them separated from roads, equipment, and people. When rocks fall, they do not always fall one at a time. They may fall as single fragments or as a group, as part of a larger volume event. The area between the toe of the slope and the bund forms the catch zone. That catch zone must have sufficient capacity to contain the volume of fallen material before it reaches the crest of the bund. If there is insufficient spacing, material can accumulate quickly and effectively reduce the working height of the bund. Once the catch zone fills, additional material encounters less resistance and can spill over the top. In addition, instead of impacting low on the bund face under controlled conditions, rocks can strike higher on the bund face or ride up along the slope and bund interface. This increases the likelihood of material entering work areas and creating a hazard for people in those areas. So when we talk about catch bund design, we are really talking about energy management. The energy generated at the top of the slope must be safely intercepted at the bottom. If the bund is too low, too narrow, or positioned incorrectly, it does not matter that it exists. It will not perform its intended function. The geometry and spacing of the bund must match the physics. But what happens when those design principles are not maintained? What happens when the bund is too small? Or when it has been partially removed? Or when it has been pushed too tightly against the base of the slope? This is where performance begins to change. If the bund is undersized, it simply does not have the height or mass required to intercept and absorb the incoming energy. Instead of stopping the rock, it may allow override. If the bund has been undercut or reduced in width, its stability is compromised. It may appear intact from a distance, but structurally, it no longer has the same resistance capacity. Under impact, it can shear, collapse, or displace. Then, in situations where the bund is pushed too close to the base of the slope, another issue emerges. If a rock reaches the bund while still carrying high kinetic energy, and the bund face is steep or relatively rigid, the impact can redirect that energy upward and outward. Instead of absorbing and dissipating energy, the bund can act like a deflecting ramp. The rock may then be projected over, beyond, or around the bund crest. When we remove the runout zone, which is the design space between the base of the slope and the start of the catch bund, we remove the opportunity for energy to be reduced before impact. That is why spacing matters. Adequate standoff distance provides room for energy dissipation before the rock reaches the bund. So, the effectiveness of a catch bund is not just about its existence. It is about maintaining the geometry that allows it to function as intended. Height, width, and spacing, when any of those are reduced or altered, the bund's ability to manage energy is reduced as well. Effective bund design is not about stopping a rock instantly. It is about managing energy. The goal is controlled dissipation, not redirection. In mining environments, poor construction and management of bunds can result in rocks traveling further than expected. Rocks clearing the bund entirely and leaving the designated catchment area. Increased risk to haul roads, equipment, and people. So although a bund may be visible in the field, its presence alone does not guarantee protection. A bund that appears adequate but does not match the physics can create a false sense of security. And this is where discipline matters. Do not push bunds closer to the slope to gain extra road width. Do not allow the base of the bund to be cut away during road maintenance. Do not reduce bund height or width to create more operating space. Every one of those actions changes the geometry, and when the geometry changes, performance changes. Correct spacing is not optional. Correct height is not optional. Correct width is not optional. These are design requirements. When we respect these principles, we reduce risk. When we alter them without engineering assessment, we potentially increase exposure to unwanted risks. So catch bund designs are not a nice to have. Geometry matters. Spacing matters. Because performance matters. And ultimately, people matter most.